Hello, everybody. Thanks for being here, and welcome to this third DTIC Integrative Research Seminar. Today, I have the pleasure to present you Professor Xavier Serra, who will talk about research highlights in his journey within the field of sound and music computing. Well, I guess that most of you probably know Xavier Serra. As one of the founders of this school, ESUP, which then gave birth to the TIC, chances are that he was here already when you arrived. But anyway, since I was asked to present him, so Xavier is an associate professor in our department, and he's the director of the music technology group. What probably you don't know is that his background, I mean, he was trained as a biologist and a guitar player. And in the 80s, he got a master in computer music and a PhD in 89 at Stanford University, with a dissertation on the spectral processing of musical sounds, which is still one of the key references in the field. I met Xavier in '91 in Montreal at the International Computer Music Conference. And I guess he was surprised to see another Catalan there. Probably I was the second Spaniard ever in this conference. I'm not sure, but obviously the first was Xavier. So he was then still at Stanford, and I was in Madrid at the CSIC, and he told me that he wanted to open a research, he wanted to do research on computer music in Barcelona next year, so he insisted that I should go there. So in '92, somehow he created the music technology group. First it was him, then we were two, and now 23 years later, we are about 50 people. So to make the story short, in '94, this small group was integrated into the Institut Universitari de l'Audiovisual, which with Xavier Berenguer, who was just starting here in Pompeu Fabra. And then it was the seed in, I would say, '98 to this ESUP. So he's, I would say, one of the founders of where we are now. So back to Xavier, I would say his main interests cover analysis, description, and synthesis of sound and music signals, always with a balance between basic and applied research, and also combining both the scientific and the more artistic side and the technological side, and I would say also with a very special focus on technology transfer. I would say, as he will show, really most of the research developed by Xavier and by most of us at the MTG has a big transfer component. And I would say really that he's one of the world gurus in sound and music computing nowadays. I mean, he has tons of publications, organizing conferences, European or different types of granted projects. He has been recently awarded with an advanced ERC for the project Commnunication, which is aimed at promoting multicultural approaches in computing music research. And I guess this will be one of the topics he will be talking us about. So thanks again for your assistance, and let's welcome Xavier. Thank you.
Okay, well, thank you, Sergi, for the presentation, and thank you, everyone, for being here and for giving me the opportunity to talk about my research. In fact, this is the first talk that really shows I'm getting old. 30 years of research, that's old. But don't worry, the idea is not to go over all that. And I will just attempt to give some highlights, to try to give a coherent story of that career by mentioning some highlights. And I don't want to talk about the funding issues, the projects I got, and what I did when and where, or about the statistics about publications. That's basically on my CV, so if you're interested in that, just feel free to go online and find it. I really want to talk about research, and of course, In this lecture, it's impossible to go into detail, so what I will do is to mainly emphasize the motivation behind some of the work I have done and some of the results that we obtained doing that. So in terms of research topics that I have covered throughout my career, I guess can be summarized in the idea of sound analysis and synthesis. That was the term that was used at the time basically I started. Then I work and I have been working a lot on modeling instruments, on modeling musical instruments, so the whole sound of a given musical instrument. And in kind of the last part, the emphasis has been a lot on information retrieval type topics of course, in music, which that means to focus on describing sounds within large collections of sounds and describing music. So let me go a bit chronologically, not strictly chronologically, but a little bit chronologically through some of these highlights in this research journey of mine. So my first published work was this article in 1986 that was done during the beginning of my PhD work at Stanford University. And I worked on synthesizing marimba sounds. So the idea was to analyze and reproduce these sounds. And this was a good challenge at that time because the modeling techniques that were around then did not really handle this type of sound that well. So my approach was to basically treat the sound of the marimba bars by combining sinusoids and a filtered white noise. So each of these sinusoids would model a mode of vibration of the bar, and the noise would model the strike of the mallet into the bar, so the more nonlinear component. And then for the resonator, that was like a kind of a physical modeling type of approach, is a delay line with a filter that would emphasize the frequency of the note of the bar. And it sounded pretty good. That was encouraging, and basically this had a big influence on my PhD thesis. And this is basically a diagram of one of the models that were part of my thesis under the supervision of Julius Smith, also at Stanford. And the idea was to generalize that decomposition of sinusoids and noise and develop a model in which an input sound could be decomposed into what could be called a deterministic component, a sinusoidal component, in this case a harmonic type of analysis. And then I guess the core of the approach was the subtraction aspect of how to be able to subtract this component, this type of signal from the original sound using spectral-based techniques. And then this residual component be modeled as an stochastic signal. So there were different approaches to the stochastic approximation, but there was this idea of modeling this residual as, again, the idea kind of a filtered white noise and having filter design issues of how to approximate this residual. And of course, the idea was to resynthesize these components and obtain a synthesized sound. And in many sounds, it worked quite well. So this resynthesized sound was quite similar to, or in many cases, identical to the original. So let me just briefly put you an example. So this is a spectrogram of a cello sound played by me. Sorry, maybe it's not so well played, but let me just play it. So then it's from this representation that we perform the deterministic plus stochastic type of analysis. So, and the idea is that we obtained a representation of the harmonics of the sound, which would be these black lines, and this would be the the deterministic component, and then this component is subtracted from the original spectrum, and then the residual is approximated with an stochastic representation, and what you see in the background is the spectrogram of this representation of the stochastic component. And then from this we can resynthesize, and as I said, for example, in this particular case, and with these speakers, you would not hear the difference. But that was not the main goal. In fact, the main goal was to be able to obtain a representation in which we could do weird things. I mean, I was in a musical context, and the idea is that you want to create new sounds. And the claim of the computer has always been that we can do any sound we can imagine. And the idea is, okay, how can we use an intermediate representation to transform the original sound and create some new sound? So this is what this sounds like. So anyway, so this shows some of the transformations, and of course I'm not going to detail the kinds of things that we can do, but we can do a lot of things. Okay, so that was basically my thesis work, and a next goal was to use it to model complete instruments. So it was clear that from this type of modeling we could actually model all the sounds of an instrument and basically build a synthesizer. And this is a diagram of a patent. It was granted as part of the work I did at the research lab in the US of Yamaha. I was working at Yamaha after my PhD. And this is a diagram of like the synthesis part of the system, in which the idea is to start from recordings, samples of an instrument. And the core part of that is to be able to factorize or model the different aspects of the sound that are generic and that you want to control for the instrument, so that a user would like to control. Okay, so that you actually build a complete synthesizer. And I work both on several instruments and also specifically on the singing voice. And that was the beginning also of quite a number of works that we did focusing on the singing voice. But one clear problem that you can see here is the complexity. This starts to be quite complex. There is a lot of control parameters, a lot of features that are correlated and that somehow need to be treated in a single way, and you cannot just play with it and create the weird sounds that we just heard. So a challenge was to, okay, how to facilitate and organize that complexity. And this is some work that I did already being at the UPF, and it was published in '97. And this was to deal with musical expression. So if we want to make a synthesizer to be expressive, that's not easy. That's one of the clear challenges in synthesis. So for this work, I collaborated with people from the CSIC, Josep Lluís Arcos and Ramon López de Mànteres, basically to incorporate AI type of techniques into handling this complexity. So Josep Lluís Arcos, as part of his PhD thesis, was working on case-based reasoning type of approaches. So what we did was to use that to create a knowledge base of what does it mean to be expressive, let's say, and learn from examples. So in this knowledge base, the idea is that we have a whole bunch of cases and models that capture the essence of expressivity. And then we can take a recording of a non-expressive sound or non-expressive musical phrase, and using this knowledge base and all these analysis synthesis techniques that I was working on, we can generate a synthesized expressive sound. So let me just put you an example. So for example, this is a phrase of a jazz phrase, a ballad, a very simple one. Let's listen to that. Okay, and then the idea is that the system had a whole bunch of examples of expressive phrases of other contexts and was able to basically propose automatically transformations to every part of the sound in order to make it expressive. So let's listen to that. Okay, so that was a good approach to handle this complexity and making sounds that sounded interesting. Another approach was to do what is called morphing. So instead of using these complex control parameters, use the controls from another source. So the goal here is to apply transformations to a sound by incorporating qualities of another sound. So with a group of students and in collaboration with Yamaha, we developed this system that was able to morph the sound of someone singing with the sound or the information from of a target sound of someone that we pre-store the recording, and then be able to morph. So we would do the alignment of the two voices using hidden Markov models for doing some phoneme-based alignment. So here we incorporated some technologies from speech processing and speech recognition to do that, but applied to the singing voice that had some specific characteristics. And then we are able to basically interpolate or morph the two sources and create synthesized sound. And of course, you can control this interpolation in different ways to make it interesting. So this was done in the context of karaoke applications for Yamaha. And the project was called Elvis. So let me play you this video from that time in which Alex Loskos, one of the students at that time, is trying the system and basically morphing his voice with the voice of a female singer. So let's listen to that.
泣きながらちぎった三振を手のひらにつなげてみるの悩みなきながらちぎった三振を
Anyway, so this was a nice demo, but in terms of marketing potential, it had a lot of problems. Especially, it was very costly to prepare all this material and all this morphing. But we knew from this work to basically synthesize, or at least to be able to emulate the singing voice. So we were able to develop a complete synthesizer, a complete singing voice synthesizer. And this was also, again, a collaboration with Yamaha and with some of the same students. This particular model was part of the PhD thesis of Jordi Bonada. And the idea here was, okay, let's, instead of having to analyze every specific sound and do morphing, let's just record a singer, bring it to the studio, record all the phonemes of a given singer, and then develop a model that captures all the voice, singing voice characteristic parameters. So we had to develop an excitation plus resonance model in which then we could parameterize things that then in the synthesis engine we could control, and the user could produce from the lyrics of a song, plus the melody could produce a synthesized version of that song. And that worked. That was the demo that we presented to Yamaha was good enough so that they decided to to make it into a product. And this is what has become Vocaloid. So Vocaloid, this is the interface of one of the recent versions of Vocaloid, in which you put the lyrics, you put the notes, and then it synthesizes. So I could spend a long time talking about Vocaloid. I think it's a fascinating story of how a given technology from a research group makes it into, I would say, a cultural phenomena, at least in Japan. So if you talk about Hatsune Miku in Japan, that's a very sort of known character. So the Vocaloid 2 came up with this character, virtual singer called Hatsune Miku, and this was the design of it. Again, I'm not going to talk about the story about that, but let me just play you this video. This was a video that someone anonymously put on a sharing online site, Nico Nico Doga from Japan. And this was a very important component of the later success of Vocaloid. So let me just play. Of course, it's not the best synthesized sound. There are other versions that are better, but from a kind of a historical and sort of impact point of view, this was quite an important video. So let me play that. But if you're interested in listening thousands or hundreds of thousands of this type of thing with better quality, better graphics, just go online and look for Vocaloid or Hatsune Miku, and you will find many things. Anyway, so out of all this work, it was clear that we had the knowledge and the tools to be able to analyze sounds and extract features of sounds. And these features started to be relevant in the emerging field of information retrieval. So the idea of information retrieval, and in the 90s, there was the initiative of MPEG-7, in which the idea was to standardize the description of multimedia content in a way that we could create repositories and be able to do automatic searches of content. So we basically saw the potential of our work into this more information retrieval type of application, and with Perfecto Herrera and with people from IRCAM, we started contributing to MPEG-7, and this is an article beginning of that. Well, this is not exactly from the article, but it's the idea of being able from this analysis data to extract features that are relevant to then describe and do applications on top of that. And this was the beginning, basically, of what we now call the music information retrieval field. This was the very beginning of the field, and the very beginning of us getting into that field. And that has been a very important kind of field of research in the MTG and internationally. So one of the bottlenecks and one of the biggest problems in sound and music, which maybe is not as important as in speech or some other fields of research related with this idea of information retrieval, is the access to collections of sounds, to large collections of sounds with which to do research. And mainly it's because of all the copyright issue that surrounds all the music industry. So early on, and this was done like more than 10 years ago. We started in 2004, and Bram de Jong was one of the first people at the MTG developing this infrastructure. We worked on developing infrastructure, so basically it's more of a software engineering type of project, with which we could crowdsource audio content, sounds, and information about the content with which we could do research. Okay? We did not publish about that. In fact, the only publication that really, the first publication that really talks about this in terms of the infrastructure is a publication from 2013, so it's clearly much later than what we started. But in here, again, the idea is to develop an infrastructure, and there is quite a lot of interesting research developments behind all these that allow people to upload sounds, allow people to organize and search for sounds, and then people can download. And there is a number of things related with text analysis and audio analysis and similarity search to be able to make all this side appealing and relevant. And this is basically free sound. Free sound has been a platform that we have been maintaining for more than 10 years now, and it has been very successful. These are some of the numbers that kind of basically statistically of the site, so it's quite large. There is a lot of activity, there is a lot of users, and for us has been a great tool on which to do research on a number of semantic web type things, machine learning type things, and sound analysis and synthesis. And in fact, this week, tomorrow, and next week, there are 2 PhD defenses from our group, basically using this infrastructure and theses that have contributed to develop this infrastructure. So it has been a very important platform for us, both, of course, useful for the community and for people, but also at the same time for our research. Then in the other description issue is this idea of music description. And in here, again, we have been doing research in describing songs, describing music for a long time, more than 10 years. In fact, this is one of the early publications I could find from 2005. And this shows the number of people at the MTG that have been working on this. And this is one of the early publications in which a lot of the research or PhD theses were basically integrated into different types of platforms, or were combined to create some useful technologies out of that. The area of music description is, of course, is a very active one. And it's still we are far from being able to solve a lot of the basic issues behind that. In this diagram, it shows a little bit of the issues. So the idea from a music retrieval point of view, we start from signals. We start from audio signals, and I guess our main emphasis is in here. But we also use, and especially more recently, other accompanying information like text or the images, or being the cover of a CD, or being the score of a piece of music. So we start from that, and the aim is to be able to generate information, descriptions that can accompany these signals, that accompany these data, and therefore we can develop recommendation, exploration, different types of applications based on that. So the idea is to, of course, at the first level, we have features that can be extracted quite efficiently from the signal using different types of techniques. And then there are more higher abstraction levels that relate more with musical concepts, and that required not just type of standard signal processing techniques, but we need to include other type of methodologies and information to get to that level. Of course, ideally, we want to go to this higher level of human expression or ways that we interact with musical content, and that we like to generate automatically from all these signals. That's in here, that's where we really started going beyond our signal processing and statistical type of approaches that we had been doing for a long time. it was clear that we couldn't reach this level of description using this methodology, so we had to start introducing machine learning, we had to start doing semantic web type of approaches, and we had to include, and this is a very important component, we had to include music knowledge, sort of the theory of music, so that we can bring kind of a top-down type of analysis that allows us to basically push this. We still, I mean, from this diagram, I basically want to show the idea that there is this concept of the semantic gap between these kind of machine-generated type of information and the human-level type of information. Of course, we would like to be able to cross that, going from this type of signal up and going from this type of more human-based semantic information down. But that's still not quite feasible. In some very specific tasks, we have been able to kind of cross that a little bit, but I would like to claim that we're still far from being able to really cross this semantic gap. But out of these, there is a lot of problems that have emerged, and let me just mention a few so that we can get an idea about all these. The first issue is, of course, we are starting to deal with, I guess now you would call big data. No? So we're starting to deal with large amounts of data, and a lot of things have to be efficiently computed, and you have to try a lot of algorithms, and you have to do a lot of machine learning based on a lot of features that you analyze and be able to identify what is more meaningful. So because of that, the development of tools that do that efficiently, that do the analysis of all this audio efficiently, was from the very beginning a fundamental task. So we have been developing tools in that direction, so in the direction of making things that are efficient and at the same modular, because I mean this is not for a product, this is for research, so you want to be able to do fast prototyping of your ideas and combine different algorithms. Again, this is another type of research, which again is more this software engineering side, which we haven't published, or at the time that we started all this development, we didn't publish that much. In fact, so this publication is very recent, but reflects a lot of work for many years, in which we have also been integrating research from many students, many PhD research work, into this library that is able to handle audio in large quantities, so it's efficient. It handles all different types of formats, I/O issues, and kind of software architectural issues to facilitate the combination of these models. And at the same time, it has specific algorithms for extracting specific features of the sound. So in this tool, this is a C++ type of library, and it includes a whole bunch of algorithms of spectral analysis, tonal analysis, rhythm, melodic analysis. So a lot of the research that many PhD students have done in the past 10 years. And then there is some Python wrapping around it that makes it quite flexible and easy to do prototyping from. So that most people basically use this Python wrapping from that. So Essentia is a free software library, so it's available in GitHub, and it's available under an open license. But we also license it commercially for so that people, companies can close it and include it into particular products. So a lot of things have emerged from that, both research projects from us and from many other institutions, and particular products by companies. And in fact, we started a company, BMAT, that basically was born from this type of software tools, and with the company we developed some specific things for Yamaha. We have developed a number of prototypes and commercial systems that are out there and that are based on this library, and we're still very much actively improving this set of tools. And now, basically, let me go to, I would say, the most recent kind of research focus that I have been having in the last few years, and is this idea of domain-specific music description. So from what I said before and the idea of the semantic gap, it's clear that the current approaches are quite have a hard time in kind of advancing in the higher level description of music. And if you look at the publications and the work in the MIR community for the past few years, it's clear that there is not much improvement at the level of automatic description of music. So my approach, and this was the first publication, and this was in 2011, and this is the beginning of a large project with this ERC grant that I obtained, in which I have been able to, let's say, to handle a large type of challenge and address some of the issues that are in the field and that are limiting. So the idea is, okay, we cannot attempt to find generic ways to describe any types of music. So let's try to use as much domain knowledge as possible of particular music traditions and find ways to model that in order to advance in the idea of this semantic analysis. So the idea is that, okay, in order to do that, well, there is a lot of topics involved. There is the topic of gathering data. I mean, all this is data-driven work, and the gathering data, as I mentioned before, it's clearly one of the bottlenecks in a lot of this research. But also, we definitely need a lot of musicological studies and music knowledge to be brought into these. In order that then we can develop a number of technologies. We need to introduce the concept of ontologies and being able to capture and formalize the knowledge of particular concepts of a particular music tradition as ontologies, so that we can drive the audio analysis type of approaches and the profiling of the community that supports a given music tradition, so that all very much interacts with each other in order to develop systems that allow to do meaningful semantic description, exploration of music collections, etc. So let me maybe talk a little bit about these things. As I said, one of the core issues is the data, the access to good data from which to do analysis. And so that's the idea of research corpora. And in any field, I guess this would be a diagram that expresses this idea of we want to study a given phenomena, in our case, a given music repertoire. And in order to study that, we need to put together a corpus that kind of captures or reflects all the essence of this repertoire, and with which we basically can study and model some task-specific problems that we need to address for this more music recommendation type of problem. And then out of these corpora, well, for a specific research task, what you do is you develop specific data sets that can be used for ground truth or for testing some particular approaches, so that you can really evaluate your algorithms in an efficient way. So this really has been a major effort for us, even though sometimes in research we consider that this is not a meaningful effort. And of course, if a PhD student has to start putting together a corpus, that can take a long time, and basically that's not feasible. And at the end, that means that a lot of the data that many people are using is not really good enough, and that really has a huge impact on the results. But we could afford it because we had this large project and a lot of people involved, so we have been able to really put meaningful research corpora. And what we have done is to this idea of domain-specific analysis, we have chosen some music traditions that are quite distinct from the kind of music we had been working on before, in a way kind of to challenge what we were doing and to see if the kind of analysis that we were doing would be able to work in some of these kind of non-Western music traditions that have characteristics that are quite distinct and quite different from Western pop music, which is the standard type of music that we normally do in MIR, or we have been using. So we have been putting together corpora. Well, these are the numbers of the recordings, but apart from the recordings, there is all the accompanying information, metadata, scores, etc., that are fundamental to capture a given music tradition. And of course, all this has been done with expert musicologists, with musicians, with people from these different cultures. And that has been, in fact, a very rewarding experience of really developing these corpora in a meaningful way. And, well, out of that, there has been a lot of research, and it's impossible. I have had, and I am working with many PhD students and collaborators on different aspects, taking advantage of this corpora that we have been putting together. This is just one example that exemplifies a little bit this type of work. And I would say that one of the core issues in when you want to do this kind of semantic analysis is the issue of similarity. Okay? We want to be able to compare things. We have entities and we want to compare things. And of course, we want to compare things in a meaningful way for some particular task. So in our work, basically the idea is, okay, we want to develop similarity measures that can be useful for a community of users, of music lovers of a particular music tradition, and when they say that two things are similar, our systems say that they are similar. And that's not obvious. For example, here, this is a particular work from the PhD thesis of Sankalp Gulati, which is still work to be pending to be published, is submitted for publication, in which we have been working on melodic similarity. So the idea is that okay, let's analyze melodies of a given corpus. In this case, these are from Carnatic music from the south of India, and for example, these are three classes of melodic motifs that someone would consider them part of the same class. Okay, so these would be three classes of motifs. And if you think of a time series type of approach, I doubt that without any extra information, you could come up with the idea that these are similar and these are similar and these are similar within them. So how do we go about that? And in fact, even to make it even more clear, let me play you three fragments. This is of Hindustani music, so north of India. This is an original little melodic motif like this one, so that would be a motif. Okay, and we want to look for similar motifs to this one. Okay, and I'm going to play to two different motifs that could be similar. So for example, this would be, let me play it again. This would be one. So if I ask you which one is similar, well, now you know a little bit the joke, but that most people would say that fragment 1 is clearly the most similar to the original, and that's not right. So if you play this to a musician of Hindustani music, they will definitely say that fragment 2 is the one that is most similar. So how do we go about basically reproducing that? So basically identifying what someone that is knowledgeable of that music tradition identifies as similar. Of course, there is a categorical perception issue here, in the sense that the melodical framework in Indian music is what we call the ragas. So you can have two melodies that might be similar, but there might be a little thing that puts that motif into a different raga. So automatically, the categorical perception of a musician will place it in a different, and that's what is happening here. So basically, this second melody is of the same raga than this first fragment. So the challenge, and again, is not a solved problem, and this is very much work in progress, is how we do data processing in which we can actually capture all that. Of course, we can do supervised type of analysis in which we obtain data from users and then use that. And normally our approach is combine both supervised and unsupervised type of approaches in order to basically develop similarity distances that take that into account. You cannot do supervised because it takes a lot of effort by musicians to create all that data. So we have been doing a whole bunch of approaches, and quite interesting, in which we want to pre-process basically these melodic contours, these time series motifs, and being able to identify what is really relevant for a particular music tradition. And again, it will be different. The type of pre-processing, the type of knowledge that you bring in, it will be different in one music tradition or another. I wanted to spend a little bit of time in this because, again, this is just one small example of what we're doing, but hopefully, I mean, it normally takes an effort for a non-music kind of audience to really see this concept of domain specific and the idea of that musical traditions might have quite different way of considering the same type of data and evaluating that data. So for example, then this is, for example, is a network in which we show our initial results of these distance measures. So here we see that, the same colors mean that they belong to the same class. Therefore, when we see clusters of each node is basically a motif, and when we see clustering of these nodes, it means that we are in the right path. That means that we have succeeded in clustering the motifs that belong to the same class that has been labeled by some musician or has been labeled in some other way. So anyway, so that's basically very much our work. And then what we are doing out of all that is basically try to combine all this with this, our goal of really making things that are useful and that can be, in fact, even evaluated and tested by actual users. This is a prototype of a website in which, this is the particular page of Carnatic music, in which we are basically integrating our research on these similarity measures and on quite a number of research topics that we are working on in order to explore these corpora for these music traditions and find ways to automatically organize and structure all this information. So there's a whole bunch of topics, and with all my PhD students and collaborators in this project, we are targeting a number of things that are beyond what I can explain here, but again, you can find publications in a lot of these, but again, this is very much current research, and hopefully we will improve quite a bit of the current results and start making some meaningful applications on meaningful tools that can be of use. Okay, so the idea of these is that we actually are useful to the community. We are useful to the musicians and to the music lovers of a particular tradition. But sincerely, with this project, we are even more ambitious than that. The idea behind this project is that we want to promote these cultural specific approaches in information technologies. Okay, so our claim is that whenever we deal with information that has cultural meaning and that is relevant and that has political implications, it has social implications, it has a lot of implications beyond the data, we cannot forget that cultural context. And we have to bring that cultural context into our research. So one of the aims here is to basically, through these, show that in a lot of the research that is being done nowadays in information technologies, culture has to be part of it. And the analysis of that cultural context, which can be handled even computationally too, but normally we don't pay attention to. Okay? So we hope to basically showcase this idea that by bringing in all this knowledge of a given culture and by being sort of close to particular cultures, and that we are not just Western, so that research doesn't have only a Western perspective. The same problem, when you look at it from a different context, has different meaning, and that has to be important in our research. So hopefully, maybe not yet, but hopefully we will be able to show that that's a very important aspect of research in order to improve, especially in this area of information technologies. And basically, to conclude, I don't want to go much further. Let me again emphasize that, of course, I was not able to talk about everything I have done. I have supervised a lot of people, especially in the last 20 years. So I had to leave a lot of the research out. So my aim was to kind of give a coherent story by highlighting a few things. And now, basically, I was trying to conclude with some identifying some trends and some things of all that work, what has happened. And maybe they're trivial, but clearly, if you look at what I have been talking about, I basically started from audio signals, and it's clearly that the research field and my work in particular has evolved into handling sound and music information, clearly beyond the audio. And in order to do that, we had to really go from audio signal processing and bring in areas that traditionally were not in our field of research. And that has been difficult because, of course, my background is in audio signal processing, so it has been hard. And this is where collaborations with people from outside our field have been fundamental and still are very much fundamental in order to help us really go into the areas of machine learning and semantic type of technologies and many others, and musicology and some others, but maybe those are not engineering fields. So I would say in general, if you look at the typical research in audio, a lot of it's going this way. So it's not something that I would say is so specific to me. And of course, finally, this idea of domain specificity. Of course, we could claim that by being in music, we're already domain specific, and that's we are happy with that. And but that's not, even that is not enough. Music is not. Many of us talk about music as a universal language. Of course, you could say music is a universal language, but there is a lot of let's say dialects that are equally important. So the need to really capture knowledge, specificity of a particular musics of particular cultures have been, I believe, the way that we have been able to advance in a lot of these more engineering and traditional type of problems. So we definitely will continue on that. And we are working on a number of projects apart from the ones I have been talking about that relate to that. And so this is it. So hopefully you got a taste of what I have been up to in my research career. But of course, all this work would not have been possible with the collaboration of many people, many students, many collaborators. I have been the luxury of being able to collaborate with a lot of people throughout this career. And of course, this would not have been possible without the support of many institutions. This field maybe For you, it sounds like it's already a consolidated, it's an important part of our department, but I can assure you that 30 years ago, that was not the case. 30 years ago, to try to convince funding agencies, convince universities, convince collaborators that to work on music was a worthwhile endeavor was not obvious. So I am really, really very happy that in this time we have succeeded in making that consolidated field, and I am proud to have been part of that. But also I want to really make a point in, I talked about research, but this research would not have been possible with the context. So in fact, a lot of my efforts, and I assume of the efforts of many researchers and professors, is making the right context for making this possible. So to be able to teach, to manage things, to organize things. And of course, most of us are here because of the research, but the research by itself, as we all know, is not sustainable unless we have the right context that supports it. And so I am really happy to have been able to make that context. And in fact, I want to thank you all for making that context. This research would not be possible with a context like what we have here. So I am proud of being in this department. Thank you. Any question?
Great, great talk. Okay, so questions, comments? Please, Horacio.
Thank you for the talk. Thank you for the talk, very interesting. So you mentioned data sets in order to be able to carry out research and evaluation. But I wonder, when you generate music, what is the evaluation methodology that you apply? So for example, if I want to, my music to produce a certain effect on the audience, how you manage to evaluate this? Mm-hmm. You obviously need humans to do that, right? So I wonder what is the methodology that you applied.
Of course, in the work we have been focusing on in the past few years, we are not into generating music. And in fact, one of the reasons has been because of that, of the difficulty of evaluating. I mean, the music is a very subjective thing. The impact on an audience is very difficult to measure. So we have been basically focused more on the actual content than on the effect on the user. Okay? Hopefully, some of these evaluations include user evaluations and get some feedback from the users, but that's really a big problem in music because there are no really very objective ways to perform that type of evaluation. So we normally develop data sets from things that there is, first of all, a very clear consensus. It's not so personalized. I mean, the idea of these music traditions is that the concept of two melodies being similar, there is a consensus. You ask two musicians, and they will tell you that they are similar, and they are similar than this other one. And that, and then, of course, in other type of problems, which for me, the concept of more emotional kind of things, I have been trying to avoid it because it's getting to be very touchy. The idea of if it's happy or sad or aggressive, there is a lot of work on music emotion. And sincerely, I have been trying to avoid that exactly because of what you're saying, because it's not that obvious to create ground truth data sets that include all that. And we are not doing that many user studies. So at the end, you need to have labeled data, and labeled data that has agreed by sufficient number of people that then you can generalize that. So there is a lot of topics that I would say escape this type of very data set, ground truth. And there again, the reason of culture. No? So you can always think of the concept of domain specificity at different levels. You can think of music being one domain. You can think of the user being another domain. What I am very interested now is at the level of the community. There is a lot of shared knowledge at a given musical culture, a given community, that can be generalized, that there is a consensus on certain things being something, meaning something, so that you can develop meaningful data sets, meaningful ground truths that are more generic than for a user, and that can advance in music analysis, because considering the whole music, if you ask an Indian person what is a happy song, or you ask an American, it's going to be different, and there's a lot of research that shows that. So that means that that's not a good approach, that we cannot just try to work on some of these descriptions or some of these analyses at the generic musical level. Any other?
So actually, coming back to this issue about similarity, when you show us this example, so it's clear that the local experts are wrong. I mean, so they are the
Of course.
So I mean, this reminds me of when children grow up. It's known, okay, that up to a certain age they can distinguish certain foreign phonemes, okay, so they can make distinctions about sounds and so on. So it looks that one thing among many, okay, is about the features. So in a certain musical context, in certain musical culture, yes, you train, okay, you learn certain features, okay, to appreciate music and so on.
Correct.
In the other context, you learn other
Correct.
features.
Correct.
So this question related to the machine learning stuff. So how do you learn these features right now? Is there an unsupervised way in which you are learning these features?
It's a combination of supervised and unsupervised. Supervised is very complicated because the annotations to do all this is not scalable, and it's not. But you can kind of play tricks. For example, one of the things we did in these melodic similarities, okay, if you look at one particular song that is within the same raga, clearly those motifs have a degree of similarity because they belong to the same class. So you can learn the similarity, that similarity, from an unsupervised way by defining the proper sort of set of data in which you extract the information, and then that can be generalized. So it's kind of defining meaningful sets in which then within that an unsupervised approach can bring or can emerge some meaningful similarities. And then of course at the end you always have to test with musicians, with users, to say if that's meaningful. Yeah, so far, especially in this melodic similarity, it has worked. And some of these things have emerged automatically from this data.
As you said, bringing culture and cultural differences in this type of analysis is really, really important. But I was actually wondering how much historical differences are actually similar to cultural differences. So if you take, for example, Western music over all the times that we know, which type of evolution is similar and where is it different?
Of course, we are restricted by our limitation of only dealing with recordings. That's where we do most of our analysis on. So the history we can analyze to do this type of historical analysis is kind of limiting, and we have not paid too much attention on this kind of historical thing. But for me, it's very interesting related to that, the fact that a typical issue is that, okay, in Western music we have written scores. So that means that we can go back and see how things evolve in time. In Indian music, it's mainly an oral tradition, or in Chinese music. So that means that, strictly speaking, we have not preserved so well, and we don't know how things sounded a few years back, or a few decades, or a century back. And interestingly enough, and there has been quite a bit of some work on that, oral traditions are able to preserve history better than written traditions. The fact of the written traditions kind of forces you to innovate, to change. And basically every composer has to add changes. And in some of these oral traditions, they adapt to the new context, but they are able to preserve this continuity. So it's really very interesting to follow, and we cannot go back that much, as I said, but how the historical evolution of these oral traditions change, and the idea of a teacher and a guru in the case of India, of how a student kind of adapts the learning from the master and then modifies. But it's interesting to see that in those cultures, they have the feeling of being very innovative in a way that is completely different from the concept of innovation in the Western world. And they innovate in another way. And so the concept of historical evolution is completely different. And we're always struck by going to some countries and seeing that the painter that they do now is not that different from paintings that they did, or at least from our eyes. But that's, again, wrong. That's a view of the West of thinking of evolution and of historical change that has nothing to do with some of these historical changes in other. The problem is with data, it's difficult to analyze these things, but it's really fascinating to look into all that.